Hello everybody, and welcome to part B of problem 9. And this is another problem of calculating the work needed to empty a tank. Okay, and so in this problem, we've got the same tank that we're looking at in figure 1. Just the difference between part A is that this time we're not filled with water, we are filled with a gelatinous goo. Is goo a word? Well, my spell checker said it is, so I guess so. And in this case, we've got a substance that doesn't have a uniform density. So in part A, we had a constant density of 1,000 kilograms per cubic meter. This time, the density is going to depend on where the goo is in our tank. Okay, so there's a function that represents our density. Okay, and the other thing is that in this case, our tank is full. That's going to be another difference from part A. Okay, but what's nice here is that the setup of this problem is going to look very similar to part A. Okay, so we're going to still think of this problem as finding the work one slice at a time. Okay, so if we just draw in kind of a typical slice and give the distance that it travels a name y, you're going to recognize the steps that we go through as being very similar. Okay, so work is force times distance. And so the first thing that we need to know is the weight of that slice. Okay, and what I'm referring to when I say slice is that guy. Okay, and the factors in that are going to be the same as they were in part A. We're going to take volume in meters cubed times density. Okay, and then round it off by multiplying by gravity. Notice again, just like in part A, when we cancel the units, the meters cubed go away, and what we get left over is kilograms meters per second squared, which is newtons. That's the correct unit of weight. Okay? So let's fill in the pieces here. The volume of that slice hasn't changed. We know that its radius is 1, so we're going to take its area, it's circular, and multiply by its thickness. So pi times 1 squared times dy gives us the volume. Now the density, in this case, is a function. Okay, so it looks like 100y plus 1,000. That's basically telling us that the bigger this distance y gets, the more dense our substance is. Okay, so it's denser towards the bottom of the tank. And we're going to multiply by the acceleration of gravity, which is still 9.8. Okay, now we can maybe simplify this a little bit here. So if we take this 9.8 and maybe move it to the front, we're going to get 9.8 pi, 1 squared is 1, times 100y plus 1,000 times dy. And units should be newtons, as we mentioned above. Okay, so there's the weight. That's the force that's involved in the problem. The other component of work is the distance. Okay, we can see from our picture that that's just going to be y meters. Okay, so to get the work then, it's going to be force times distance. So we'll take the weight that we calculated above, multiply by the distance. Okay, and so what I've written down so far would be the work needed just to move that one slice to the top. To get the total work, we need to integrate, add up all of the work contributions from each of those slices. And the question then would be, what are our limits of integration? Okay, well, that's like asking, what are the range of y values that our slices could travel? Okay, if you look back at the picture for a minute here, this time the tank is full, and so the range of distances that we could get is 0. Okay, that slice at the top doesn't need to move at all, and then at the very bottom, that slice has to move the entire 5. Okay, so our range of distance is just going to be 0 to 5 in this case. All right, and we just need to calculate that integral, and we'll be done. Okay, so how about if we take the 9.8 pi and factor it out, and then what's left is 100y plus 1,000 times y. We can distribute the y through. Okay, to get that, now we're ready to get our antiderivative. So we're going to get 100y cubed over 3 plus 1,000y squared over 2, that's going to be 500y squared, evaluated between 5 and 0. Okay, and then it's really just a matter of taking those limits and substituting them in. Okay, so there's our upper limit. Okay, substitute 5 in for your y's and your lower limit. We're just going to get zeros in both cases. Okay, and I'll let you confirm that when you substitute this into your calculator, what you wind up with is 513,127, and again, those units should be newtons times meters, otherwise known as joules. And there's our work.